The following is an Encore presentation of Everything Everywhere Daily.
If you take a look at the periodic table of elements, you'll notice something interesting. Go to the bottom and take a look at any element over, say, number 94. You'll find a bunch of elements that you've probably never heard of. But don't worry, because most chemists probably aren't familiar with them either. They're not part of any chemical compounds, can't be found in nature, and most of them have only existed for a fraction of a second. Learn more about transuranium elements, what they are, and how we even know they exist on this episode of Everything Everywhere Daily. This episode is sponsored by Mint Mobile. Do you know what doesn't belong in your summer plans? Getting burned by your old wireless bill. While you're planning beach trips, barbecues, and 3-day weekends, your wireless bill should be the last thing holding you back. And that's why I use Mint Mobile. With plans starting at $15 a month, Mint Mobile gives you premium wireless service on the nation's largest 5G network. The coverage and speeds you're used to, but just less money. So while your friends are sweating over data usages and surprise charges, you'll be chilling, literally and financially. With Mint Mobile, you can use your same phone number, and contact list, and even connect to the exact same towers and cellular networks. The only difference is the price. This year, skip breaking a sweat and breaking the bank. Get your summer savings and shop premium wireless plans at mintmobile.com/EED. That's mintmobile.com/EED. Upfront payment of $45 for 3-month 5GB plan required, equivalent to $15 a month. New customer offer for first 3 months only, then full price plan options available. Taxes and fees extra. See Mint Mobile for details. This episode is sponsored by Planet Money. Tariffs, meme coins, Girl Scout cookies, what do they all have in common? Money. Economics is everywhere and everything, fueling our lives, even when we least expect it. If you're a fan of Everything Everywhere Daily and are curious to learn something new and exciting about economics every week, I recommend you listen to the Planet Money podcast from NPR. What I like about Planet Money is that I can get an update on the week's financial news in about 30 minutes. Stories like the adoption of stablecoins or the price of eggs. From the job market to the stock market to prices at the supermarket, Planet Money is here to help explain it all. The Planet Money hosts go to great lengths to help explain the economy. They've done things like shot a satellite into space, started a record label, made a comic book, and shorted the entire stock market. All to help you better understand the world around you. Tune into Planet Money every week for entertaining stories and insights about how money shapes our world. Stories that can't be found anywhere else. Listen now to Planet Money from NPR. Over the course of this podcast, I've done many episodes on individual elements of the periodic table. The episode will usually talk about its atomic configuration, how the element was discovered, and its various uses. The transuranium elements, however, are in a category all of their own. They barely exist naturally, are all highly unstable, and their very existence is due to human creation. With some minor exceptions, they don't have any use at all, and for the most part, they don't even exist save for a tiny fraction of a second. But let's start by explaining what a transuranium element is. The heaviest naturally occurring element in nature is uranium, with an atomic number of 92. Uranium isn't incredibly abundant, but it isn't hard to find in rocks in many places around the world. Having an atomic number of 92 means that there are 92 protons in the nucleus of the atom, and the number of protons is what determines what an element is. While each atom of an element have the same number of protons, different atoms can have different numbers of neutrons in the nucleus. Atoms with different number of neutrons are called isotopes. In the case of uranium, there are 2 common isotopes that are found in nature: uranium-238 with 146 neutrons, and uranium-235 with 143 neutrons. Chemically, isotopes behave exactly the same. However, different isotopes will have different levels of atomic stability. The more unstable an atom is, the more likely it is to undergo radioactive decay. There are only certain isotopes of any element that are stable. With the wrong configuration of protons and neutrons, it'll fall apart until the resulting configuration is stable. The statistical time it takes to fall apart is known as its half-life. Extremely unstable atoms may have half-lives of just a fraction of a second. More stable atoms like uranium can have half-lives in the hundreds of millions to billions of years. The other thing to know for the purpose of this episode is that, in general, larger atomic nuclei tend to be more unstable. That's not to say that you can't have a rare isotope of a lighter element be unstable, but you usually won't find those in the environment because they've already decayed. So, that brief explanation of nuclear physics aside, going into the 1940s, there were no known elements with an atomic number higher than uranium at 92. There was nothing found in nature that had an atomic number higher than that. There were some claims of an element 93, but there was no proof. So, as far as everybody knew, that may have been the heaviest element in the universe. However, in 1940, experiments were conducted with nuclear fission by a team led by Edwin McMillan and Haig Abelson at the University of California, Berkeley, who bombarded uranium-238 with neutrons. This created uranium-239, which then decayed into a new element, number 93. The element was dubbed Neptunium, because the planet Neptune is the one after Uranus. However, they realized that if element 93 existed, then it also must decay into element 94. Element 94 was discovered in 1941 by a man whose name is going to appear a lot in this episode, Glenn Seaborg. Seaborg worked at Berkeley, and their process was very similar to that which discovered neptunium. I've previously done an entire episode on plutonium, but the one thing I'll add for this episode is that extremely trace amounts of plutonium and neptunium have been found naturally as the result of decay of uranium. However, the amounts are so small, literally scattered atoms, that for all practical purposes you can still say that uranium is the heaviest natural element. The quest to create more elements continued. In 1944, as part of the Manhattan Project, Glenn Seaborg's team discovered element 96, curium, named after Marie Curie, and element 95, americium, named after the United States. Both elements were created by exposing plutonium to either alpha radiation or neutron radiation. Both americium and curium actually do have limited practical uses. Americium is sometimes used in smoke detectors as a source of ionizing radiation, and curium is sometimes used to kickstart fission chain reactions. What little that is needed is usually a byproduct of nuclear reactors. This technique of exposing heavy elements to radiation continued to bear fruit in discovering new elements. Seaborg's team discovered element 97 in 1949, berkelium. This was created by exposing americinium to alpha radiation, and then element 98, californium, was created by exposing curium to alpha radiation. Berkelium has no known use whatsoever, and californium can be used in small amounts to also kickstart nuclear chain reactions because it is a strong neutron emitter. In 1951, Glenn Seaborg was awarded the Nobel Prize in Physics for his discovery of transuranium elements. However, this was nowhere near the end of the creation of elements with ever larger atomic numbers. In 1952, researchers at Berkeley went through radioactive debris from hydrogen bomb tests on Bikini Atoll. They discovered over 200 atoms of element 99, which was dubbed Einsteinium, named after Albert Einstein. The next year, debris from a detonation on the Iwanitak Atoll showed evidence of element 100, which was dubbed fermium, after the nuclear pioneer Enrico Fermi. These two elements can be created in a nuclear reactor, but the higher up you go in atomic number, the more difficult it becomes by over an order of magnitude along each step of the chain. For example, it takes 10 grams of curium to make 1 picogram of fermium, and a picogram is 1/1,000,000th of a gram. All of these heavier elements are very radioactive with very short half-lives. It's entirely possible that these elements could have been created in a supernova, like all the heavy elements we experience on Earth, but they wouldn't have survived very long because of their short half-lives. In 1955, element 101, mendelevium, was discovered, which was created by bombarding Einsteinium with alpha radiation, and this was also created by Glenn Seaborg and his team. By this time, exposing heavy elements to radiation had pretty much reached a dead end. A new technique was developed, which involved slamming transuranium elements with much larger atomic nuclei than just helium, which is what alpha radiation is. In 1961, the team at Berkeley discovered element 103, lawrencinium, by bombarding californium with boron atoms. Pretty much every new discovery of a transuranium element at this point had been made at the University of California, Berkeley. The next discovery was the first outside of the United States. In 1965, the Joint Institute for Nuclear Research in Dubna outside of Moscow discovered element 102, nobelinium, by bombarding uranium with neon atoms. This element was named after Alfred Nobel, the founder of the Nobel Prize. In 1969, the Soviets created element 104, rutherfordium, created by bombarding californium with carbon atoms and also created by bombarding plutonium with neon atoms. And this was named after Ernst Rutherford, who discovered the atomic nucleus. I should note at this point, the elements being created were extremely small in numbers, and they were all incredibly radioactive with very short half-lives. The first isotope of rutherfordium created had a half-life of 5 seconds. This technique of bombarding atoms with other atoms to create new elements is the technique that's still pretty much used today. The Soviets created element 105, dubnium, in 1970, named after the city where their research center was located in Russia. Berkeley created element 106 in 1974 called seaborgium, in honor of Glenn Seaborg. After this, the next several new elements were created by researchers at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany. In 1981, they created element 107, borium, named after Niels Bohr. In 1982, they created element 109, meitnerium, named after Lisa Meitner, one of the discoverers of atomic fission. In 1984, they made element 108, hafnium, named after the German state of Hesse. A decade later, in 1994, they created element 110, Darmstadtium, after the city of Darmstadt, Germany, and element 111, Röntgium, named after Wilhelm Röntgen, the discoverer of X-rays. In 1996, they created element 112, Copernicum, named after the astronomer Copernicus. After almost 20 years of new element discoveries, the crown returned to Russia and the Joint Institute for Nuclear Research. In 1999, they discovered element 114, flavorium, named after the physicist Georgy Flyarov. In 2000, they discovered element 116, livermorium, named after the Lawrence Livermore National Laboratory in California. In 2002, they created element 118, oganesson, after Yuri Oganessian, the Russian counterpart of Glenn Seaborg. And you'll notice that the elements they discovered are not in order of atomic number. Element 115 was created in 2003, dubbed Moscovium after Moscow. Element 113 was independently discovered by the Russians and a team in Japan and was named Nihonium after the Japanese name for Japan. And finally, in 2009, the Russians created element 117, which was dubbed Tennessine after the state of Tennessee, the home of Oak Ridge National Laboratory. And that is all that's been discovered as of this recording. There are periodic tables out there with placeholders for the undiscovered elements from 119 all the way up to 168. So having read off this list of elements that literally nobody would bother memorizing unless you happen to work in the field of super heavy chemical elements, what's the point of all this? All of these elements, at least beyond element 98, californium, have half-lives so short that they only exist for a tiny fraction of a second, and quantities that are so small you couldn't even tell they existed without incredibly sensitive equipment. While I rattled off the discovery dates of these elements, other researchers have been searching for different isotopes of many of these elements to see how long their half-lives are. Most are incredibly short, but some are the better part of a minute or even several minutes long. The first discovery of an element gets the headlines, but what people are really searching for is something that Glenn Seaborg dubbed the island of stability. The island of stability would be some heavy element, or more accurately, a particular isotope of a heavy element, that would be relatively stable or at least have a very long half-life. The problem with heavy atoms is that inside the nucleus there are two opposing forces at work. The electroweak force wants to push protons apart because they have the same electrical charge. However, the strong nuclear force binds them together. Over very short distances, and I do mean very short, the strong force is more powerful than the electroweak force, and thus the nucleus of an atom can exist. However, as an atomic nucleus gets bigger, the distance between some of the protons increases, decreasing the strength of the strong nuclear force. And this is believed to be why large atoms tend to be so unstable. It's believed, or at least hoped, that a configuration of neutrons exists that would provide stability to a large atom. Based on the mathematics of how isotopes of other atoms behave, it's thought that one of the best hopes for a stable large atom would be an isotope somewhere in the elements 114, 120, or 126. However, 120 and 126 haven't been discovered yet, but researchers in Dubna, Russia are working on creating 119 and 120 as I record this. If an island of stability could be found, it could usher in a new understanding of the atom, as well as maybe a new era in material science. Finding the island of stability, if it even exists, will take a lot of work and a lot of time. So the next time you take a look at the periodic table, look down near the bottom and give a moment to the elements that were created in a laboratory only to exist for a fraction of a second. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Austin Oakton and Cameron Kiefer. I want to thank everyone who supports the show over on Patreon. Your support helps make this podcast possible. I'd also like to thank all the members of the Everything Everywhere community who are active on the Facebook group and the Discord server. If you'd like to join in the discussion, there are links to both in the show notes. And as always, if you leave a review or send me a boostagram, you too can have it read on the show.